Hello, and I'm going to be making a presentation on porphyry-type deposits today. So what are porphyry-type deposits? Porphyry-type deposits are polymetallic deposits containing copper and other metals. These deposits are typically large, although they can range from 100 million to 5 billion tons of ore. These are major mineral deposits, and they are extracted for many different minerals, including copper, molybdenum, gold, and silver. Minor minerals include lead, zinc, tin, and tungsten as well. Each different porphyry deposit has a unique amount and different concentrations at different depths, and this will be explained later in the presentation. These different deposits are large enough to be mined for multi-year to multi-decade long production, and therefore are extremely valuable to an economy. So first off, where do most porphyry type deposits occur? Primarily, these porphyry deposits occur only along areas of convergent plate boundaries, although they can also exist at extinct convergent plate boundaries as well. Primarily, we are going to be looking at the ones that are found along the Pacific side of the US and Canada. So, where are these porphyry deposits formed? So, as mentioned, the plate margin, they occur at convergent plate margins where oceanic crust is submerged under continental crust. So, the example I gave was the North American West Coast. So, what happens? These In these convergent plate boundaries, the mantle that is being the plate that is being subducted is melted and then allows for this magma to rise to the surface in what is called a magma chamber. When the magma interacts with the surrounding rock, it creates contact metamorphism in different intrusive igneous rocks. This contact metamorphism is the area around where the mineral and ore deposits form. Within the magma chamber, hot fluids are percolated along inside the magma as well as around it, which allow for different metals and brines to be picked up and precipitated out of the cooling fluid. So this is how the porphyry mineralization occurs. Crystallization at the top of the magma chamber allows for the release of water and gas. This high pressure steam moves the metals from the top or the exterior of the magma chamber and moves them into and the walls of the ore lithology. Once the steam reaches an area where it is cooler, it cools and then allows for the metals to settle into these metallic rich brines. Primarily, you find copper and molybdenum deposited within the steam. Although when the pressure decreases, or as temperature decreases, so will the steam carry zinc and lead. So there are three areas that mineralization can occur in a porphyry deposit. The primary one, as we talked about, is when the hot magma interacts with the surrounding rock. This small interaction of the hot magma and the cooler rock allows for only a small amount of metal to be deposited within the ore-rich zones. Secondly, and a little bit higher mineralization is the deeper high grade or higher grade mineralization. This occurs near the top of the mantle if there is a plume located inside the crust. If this plume is located at the right depth within the crust, it will allow for steam to collect and deposit the minerals at the top of that magma chamber. And finally, the highest grade deposit is when this type of plume is located near the surface. when it is located near the surface, these different meteoric waters or rainwaters can percolate down into the magma and create a higher amount of steam, which then allows for increased reduction reactions, creating higher concentrations of mineralization. And this produces the highest metal compositions of 5 to 10%. So as we can see, the high grade mineralization occurs closest to the surface. This is because rainwater has to interact with the different mineralization, and if this water, the the different ore body has to be located close enough to the surface to have this interaction with this ore body. The lower grade mineralization is found within the surface, but this is because it is not being affected by the rainwater and it is not deep enough to have de to have dehydrated the older minerals. So this is in the area where you would find the lower grade minerals. Although you can also have the deeper high grade mineralizations. This occurs at the top of the mantle and not within the crust as dictated by the sandstone and limestone layers. This is showing a mantle plume that is separated from the general magma chamber. This allows for the steam and the heat to collect at the top of the chamber and allow for mineralization to occur due to the percolating hot liquids that are evaporating at the top of that deeper high grade magma chamber. So what type of ore, or what are the rock types that can be deposited in this ore body? Well, it is very much dependent on the host rock that the magma intrudes into. The magma intruding into the ore body also can dictate the proportion of the metal that will be precipitated. Another factor is the temperature of the deposit. If the magma is sourced from a high temperature deposit, or it can be traveling from a far distance away. So depending on the temperature of the magma and the temperature of the surrounding magma chamber, the ore around the magma chamber, can dictate how much deposition there is. These magmatic interactions with the hot fluid and the colder surrounding lithologies allows for different interactions to occur. These interactions allow for breaking of the surrounding lithologies, which allow for breccias, skarns, and epithermal deposits to form. The hot steam created by these magma chambers can also crack the surrounding host rock, which allows for veinlets of the magma to encapsulate into the rock, which then allows for different fluids to circulate along the edges of those veins or veinlets, allowing for more minerals to form, including biotite and chlorite. So now as we talked about these different alterations, we can talk about a little bit about the different alteration zones around this percolating body that is allowing for this hot magmatic mass to intrude into a colder lithology. Once the mineralization starts occurring, we will start to find out that there is these different alteration zones, which can be found by the different alteration minerals that are deposited. In this example, they're in the porphyritic alteration. We find chlorite, epidote, and carbonates, while in the phyllic alteration zone, we're finding quartz, cerussite, and pyrite. Therefore, we are finding the unaltered porphyry at the bottom with the different alteration zones coming up. We find that our ore zones are primarily located within our potassic alteration and at the edges of our pyrite shell and our porphyritic alteration. These are the areas that the different hot steam allows to percolate through and deposit the highest amount of metals. So the different metals that we are finding in the porphyry type deposits primarily include copper. This copper has a bright pink or yellow with high reflectance. And the color in hand sample can be copper red when it's fresh, or dull brown or bluish if it's oxidated. This copper is primarily mined uh, in, in chalcopyrite and then separated through chemical reactions. Gold. So gold is another native metal, and it is found primarily within or uh, could be disseminated or found alongside the different sulfides in the sample. Uh, and its primary color is gold yellow, and when it is in a sample, it cannot be tarnished. It is always has that bright gold color. Next is molybdenum. So molybdenum primarily forms as a sulfide, molybdenum sulfide, and the color is usually light gray in hand sample. And the final, more of a tertiary, less seen in porphyry deposits, is silver. Silver has the affinity to mineralize alongside sulfides, and the color is a silvery white color. And it is also found with the minor minerals in the porphyries, including lead, zinc, tin, and tungsten. So talking about the different textures of the different ore bodies, we can find a porphyritic texture, which is when we're having two different mineral sizes. This is when there was two separate equilibrium states, which means the first equilibrium state, we had a larger mineral that formed at a deeper, cooler rate, then was carried up the magma chamber and then cooled again at a second equilibrium texture, which allowed for the ground mass to form around it. Therefore, the phenocrysts are the larger, slower, or deeper cooled mineral, and the ground mass is the smaller, finer grained surrounding minerals around it that equilibrated at a lower temperature. And finally is a brecciated texture. So a brecciated texture occurs when there are large angular fragments with a matrix of smaller particles. So this usually happens when a hot lava breaks up a wall rock into blocks and allows for the magma to penetrate into it. When this happens, the magma reincorporates the different blocks into the lava flow, and then when it is cooled, it has this irregular looking shape because the magma invaded the wall rock and then allowed it to cool, which then formed this shape. And that's the end of this project. I'd like to thank you and have a good one.